Welcome. As the day gently recedes, we invite you to settle into a space of calm contemplation. Tonight we embark on a journey through 100 things physics still can't explain, exploring approximately 100 fascinating facts that reveal intricate patterns, subtle wisdom, and profound beauty within the universe's most enduring mysteries. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge flowing without demanding effort or attention. We will observe the intricate dance of fundamental forces, the subtle adaptations of reality, and the quiet wisdom embedded in the very fabric of existence, even where our understanding falters. Each unexplained fact is a small window into the vast and interconnected tapestry of physics, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. We delve not into what we know, but into the profound depths of what we are still learning, what remains just beyond our grasp, the beautiful, humbling frontiers of scientific inquiry. We begin our journey by looking outward, into the vast expanse of the cosmos, where some of physics' most profound and tantalizing questions reside. These are the mysteries that shape galaxies, dictate the universe's fate, and challenge our very conception of reality, inviting us to ponder the limits of our current understanding. Dark matter, the unseen architect. One of the most significant mysteries in modern astrophysics is the existence of dark matter. Research indicates that approximately 27% of the universe's mass-energy content is composed of this enigmatic substance. Scientists have observed its gravitational effects on visible matter, such as stars and galaxies, causing them to rotate faster than expected based on their luminous mass alone. Without dark matter, galaxies would simply fly apart. However, dark matter does not interact with light or other forms of electromagnetic radiation, making it invisible to telescopes. It also does not appear to interact strongly with normal matter, passing through us and everything around us without detection. Current theories propose that dark matter consists of exotic, as yet undiscovered particles, but despite decades of dedicated experiments, no direct evidence of these particles has been found. Its precise nature remains one of the greatest puzzles, challenging our standard model of particle physics and cosmology. The search for dark matter continues, hinting at a hidden architecture that binds the cosmos. Dark energy, the accelerating expansion. Complementing the mystery of dark matter is dark energy, which constitutes an even larger portion of the universe, estimated at around 68%. This mysterious force is believed to be responsible for the accelerating expansion of the universe. Observations of distant supernovae in the late 1990s provided compelling evidence that the universe's expansion is not slowing down due to gravity, as previously thought, but is actually speeding up. This acceleration cannot be explained by any known form of matter or energy. Current understanding suggests dark energy might be a property of space itself, a cosmological constant as proposed by Einstein, or perhaps an entirely new dynamic field. However, the theoretical value for the energy density of empty space is vastly different from the observed amount of dark energy by a factor of 10 to 20, making it one of the most perplexing discrepancies in physics. The true nature of dark energy dictates the ultimate fate of the universe, yet it remains almost entirely unknown. The origin of the universe before the Big Bang. While the Big Bang theory successfully describes the evolution of the universe from a hot, dense state, it does not explain what initiated this state or what, if anything, existed before it. The theory outlines the expansion of space and time from an initial singularity, but the physical laws we know break down at this point, preventing us from understanding the conditions or causes. It remains unclear whether the universe emerged from nothing, or if it is part of a larger cyclical process, or perhaps a component of a multiverse. Some researchers propose theories like cosmic inflation, which describes a period of rapid expansion immediately after the Big Bang. But even inflation requires specific initial conditions that are not fully explained. The question of ultimate origins, what truly sparked the universe into being, continues to elude a complete scientific explanation, pushing the boundaries of philosophical as much as physical inquiry. The arrow of time. Why only forward? Physics equations at their fundamental level are largely time-symmetric. They work equally well whether time flows forward or backward. Yet in our everyday experience, time undeniably moves in only one direction, from past to future. This is known as the arrow of time. We remember the past, but not the future. Cups break but do not spontaneously reassemble. This irreversibility is often linked to the second law of thermodynamics, which states that entropy, or disorder, always increases in a closed system. However, this statistical law describes a tendency, not an absolute prohibition on time reversal. It remains unclear why the universe began in such a low entropy state to allow for this continuous increase, creating the unidirectional flow we perceive. Some theories suggest a connection to the Big Bang's initial conditions, while others ponder if the arrow of time is a macroscopic phenomenon that emerges from complex systems rather than a fundamental property. Quantum gravity, unifying the realms. One of the most ambitious goals in theoretical physics is to reconcile general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which governs the behavior of matter and energy at the subatomic level. These two pillars of modern physics are incredibly successful in their respective domains, but they are fundamentally incompatible. General relativity treats space-time as a smooth, continuous fabric, while quantum mechanics suggests that everything, including space-time, should be quantized into discrete packets. At extreme conditions, such as within black holes or at the very beginning of the universe, both theories are needed, yet they yield contradictory results. Theories like string theory and loop quantum gravity attempt to bridge this gap by proposing new frameworks, but none have yet been experimentally verified. The absence of a consistent theory of quantum gravity means our understanding of the universe's most extreme environments remains incomplete. The black hole information paradox, what is lost? Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. According to general relativity, anything that falls into a black hole is lost forever, its information seemingly destroyed. However, quantum mechanics, particularly the principle of unitarity, states that information can never truly be destroyed, only transformed. This fundamental conflict is known as the black hole information paradox. Stephen Hawking's discovery of Hawking radiation, suggesting black holes slowly evaporate over immense timescales, further complicated the issue. If a black hole evaporates and the information is truly lost, it violates quantum mechanics. If the information somehow escapes, the mechanism is unknown and revolutionary. This paradox points to a deep misunderstanding at the intersection of gravity and quantum theory, challenging our most basic assumptions about the universe. The multiverse, our universe, one of many? The concept of a multiverse proposes that our universe is just one of many, perhaps an infinite number, existing in parallel. This idea arises from several theoretical frameworks, including inflationary cosmology, which suggests that the rapid expansion of space after the Big Bang could have created multiple bubble universes. Another idea comes from string theory, where different ways of compactifying extra dimensions could lead to different universes with varying physical laws. The many worlds interpretation of quantum mechanics also posits a branching multiverse, where every quantum measurement creates a new universe. While these theories offer intriguing solutions to certain cosmological puzzles, such as the fine-tuning problem why our universe's constants are just right for life, the existence of other universes is currently untestable and purely speculative. It remains a fascinating possibility that physics cannot yet confirm or deny. These cosmic enigmas remind us that the universe is far more mysterious and complex than we can currently grasp. Each unanswered question invites us to look deeper, to expand our perception of what is possible, and to acknowledge the profound beauty in the unknown that surrounds us, ever present in the quiet vastness of space. We journeyed through the cosmic enigmas, those vast, shimmering questions that stretch across the canvas of the universe, reminding us of how much remains veiled in starlight. Now we invite you to draw your gaze a little closer to the intricate patterns woven into the very fabric of existence, to the subtle wisdom hidden within the particles that compose our world, and to the profound mysteries that lie closer to home within the very nature of reality itself. We move from the grand scale of galaxies and the birth of time to the perplexing behavior of the subatomic, to the fundamental constants that govern our being, and to the enigma of consciousness that allows us to ponder it all. Our exploration continues with questions that challenge our most cherished assumptions about what is real, what is fundamental, and what it means to observe. Let us settle deeper into this gentle current of knowledge, allowing these profound uncertainties to wash over us, inspiring not anxiety, but a quiet sense of wonder. 1. The matter-antimatter imbalance, a cosmic anomaly. We begin with a question of cosmic proportions, yet one rooted in the most fundamental particles. Why does anything exist at all? From our theories, from the elegant symmetries of physics, we expect that the Big Bang, the universe's fiery genesis, should have forged matter and antimatter in perfectly equal measure. Each particle of matter, in its very essence, possesses an antimatter counterpart, identical in mass, but opposite in charge and other quantum properties. When these two meet, they annihilate each other in a brilliant flash of pure energy, leaving nothing but photons. If this perfect symmetry had held true, if the scales had been balanced, our universe would be an empty sea of radiation, devoid of stars, planets, or indeed us. Yet here we are, undeniably composed of matter, existing in a universe overwhelmingly dominated by it. The very existence of galaxies, of nebulae, of the earth beneath our feet, and of the intricate biological machinery that allows us to breathe and think, stands as a testament to a profound cosmic imbalance. For every billion pairs of matter and antimatter that annihilated in the early universe, there must have been just one extra particle of matter left over, 1 in a billion. This tiny, almost imperceptible asymmetry is the reason for everything we perceive, everything we are. This crucial deviation from expectation, known as baryogenesis, remains one of physics' most enduring and perplexing puzzles. Where did this slight excess of matter come from? What subtle mechanism tipped the scales? Theories abound suggesting new particles, new forces, or even fleeting moments in the early universe where the fundamental symmetries were momentarily broken. Perhaps there was a slight difference in how matter and antimatter decayed, or perhaps conditions in the primordial plasma favoured one over the other. But despite decades of dedicated research and experiments that meticulously probe the behaviour of particles and antiparticles, the precise mechanism, the unseen architect of this fundamental asymmetry, continues to elude us. We are left to ponder this delicate cosmic preference, the subtle tilt that allowed our universe, vibrant and teeming with life, to emerge from the void. It is a mystery that resonates with our very existence, a silent question whispered by every star. 2. The hierarchy problem, gravity's peculiar weakness. As we contemplate the fundamental forces that sculpt our reality, a profound disparity emerges, a puzzle so striking that it has driven physicists to imagine dimensions beyond our perception. This is the hierarchy problem, the baffling observation that gravity, the force that binds galaxies and holds us to the Earth, is extraordinarily weak compared to the other fundamental forces. Consider the electromagnetism that lights our cities and holds atoms together, or the strong nuclear force that binds quarks within protons and neutrons, or the weak nuclear force responsible for radioactive decay. These forces are immensely powerful. The electromagnetic force, for instance, is so potent that a tiny magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. Think about that for a moment. A small handheld magnet defying the gravitational might of an entire planet. The disparity is staggering, a factor of 10 to the power of 36, or even 10 to the power of 40, depending on the forces being compared. This immense gap, this hierarchy of strengths, feels utterly arbitrary, a cosmic coincidence without explanation. Why should gravity be such a feeble whisper compared to the thunderous roar of the other forces? In the elegant tapestry of physics, where symmetries and fundamental principles often dictate the behavior of nature, such a colossal discrepancy feels deeply unsatisfying. It suggests that something fundamental is missing from our understanding. Theoretical physicists have proposed various solutions to this enigma, each more imaginative than the last. One prominent idea involves the existence of extra spatial dimensions, dimensions beyond the three we perceive. In this scenario, gravity, unlike the other forces, might be leaking into these hidden dimensions, diluting its strength in our observable universe. Imagine a water hose with tiny holes along its length. Much of the water escapes before it reaches the nozzle. Similarly, gravity's influence might extend into these unseen realms, weakening its apparent strength in our four-dimensional spacetime. Another hypothesis, supersymmetry, suggests that every known particle has a heavier, as yet undiscovered superpartner, and the interactions of these partners could naturally explain the hierarchy. Yet despite decades of searching, neither extra dimensions nor superpartners have been definitively observed. The hierarchy problem remains a humbling frontier, a potent reminder that the universe holds secrets even in its most fundamental interactions, gently urging us to look beyond our current models and embrace the possibility of a reality far richer and more complex than we can currently grasp. 3. The quantum measurement problem, reality's shifting sands. As we delve deeper into the microscopic realm, the world of quantum mechanics reveals a profound mystery that challenges our very notion of objective reality, the measurement problem. Here, at the heart of the smallest scales, particles do not behave as solid, definite objects, but rather as shimmering probabilities, existing in multiple states simultaneously, a phenomenon known as superposition. An electron, for instance, might be spinning both clockwise and counterclockwise at the same time, or be in several locations at once. This isn't just a lack of knowledge on our part. The particle genuinely embodies this ambiguity. The perplexing part arises when we try to observe these quantum entities. The moment we measure a quantum property, the spin of an electron, the position of a photon, the superposition abruptly collapses, and the particle settles into a single, definite state. It's as if the act of looking forces reality to make up its mind. But what constitutes a measurement? Does it require a conscious observer, or merely an interaction with a macroscopic instrument? Where is the boundary between the quantum realm of probabilities and the classical world of definite outcomes? This question, often illustrated by Schrödinger's famous thought experiment involving a cat in a box that is simultaneously dead and alive until observed, strikes at the core of what we consider real. Is the universe inherently indeterminate until a conscious act of observation solidifies it? Or is there a more subtle, yet to be understood physical process that governs this collapse, perhaps involving gravity, or an interaction with the environment that effectively measures the system? Numerous interpretations attempt to resolve this paradox. The Copenhagen interpretation, one of the oldest, simply states that the act of measurement causes the collapse, without explaining how or why. The many worlds interpretation suggests that every possible outcome of a quantum measurement actually occurs, each in its own parallel universe, leading to an ever-branching cosmic tree. Other theories propose objective collapse models where the superposition naturally breaks down over time or due to some fundamental physical threshold independent of an observer. Yet, despite these ingenious attempts, the measurement problem remains unsolved, a persistent thorn in the side of quantum mechanics. It forces us to confront the uncomfortable truth that our understanding of reality, particularly at its most fundamental level, is incomplete. It invites us to sit with the strangeness, to appreciate the profound mystery of a universe that seems to hold its breath, waiting for us to look before deciding what it truly is. It's a reminder that perception itself might be an active participant in shaping the world around us, a deeply meditative thought that blurs the lines between physics and philosophy. 4. The fine-tuning of the universe. A cosmic coincidence? As we continue our gentle journey into the unexplained, we encounter a mystery that whispers of profound design, or perhaps of an unimaginably vast cosmic lottery, the astonishing fine-tuning of the universe. We speak of the fundamental constants of nature, the gravitational constant, the strength of the electromagnetic force, the mass of the electron, the cosmological constant that governs dark energy, and countless others. These are not arbitrary numbers. They are the precise dials and settings that dictate the very possibility of stars, galaxies, chemistry, and ultimately life itself. Consider for a moment the delicate balance. If the strong nuclear force were just a few percent weaker, atomic nuclei would not hold together, and no elements heavier than hydrogen could form. If it was slightly stronger, hydrogen would have fused into helium too quickly in the early universe, leaving no fuel for stars to burn long enough to synthesize heavier elements. If the electromagnetic force was slightly different, atoms wouldn't form stable bonds, or planets wouldn't be able to retain atmospheres. And if the cosmological constant, the elusive dark energy, were just a tiny fraction larger, the universe would have expanded so rapidly that matter would never have coalesced into galaxies and stars. If it was slightly smaller, the universe might have collapsed back on itself long before life could emerge. The probabilities of all these constants falling within the incredibly narrow life-permitting ranges are astronomically small, leading many to marvel at this apparent cosmic coincidence. Is it truly just a fluke, an improbable roll of the dice in a vast, indifferent cosmos? Or does it point to something deeper? Some interpretations suggest that this fine-tuning is evidence of a multiverse, a concept we touched upon in our previous journey. If an infinite number of universes exist, each with different physical laws and constants, then it becomes statistically inevitable that at least one of them would possess the precise conditions necessary for life to arise. We simply happen to inhabit that particular fortunate universe. Another perspective, the anthropic principle, suggests that the universe must have the properties it does because if it didn't, we wouldn't be here to observe it. This, however, doesn't explain why those properties exist, only why we perceive them. The mystery of fine-tuning invites us to contemplate the sheer fragility and preciousness of our existence. It asks us to consider whether our universe is a unique, exquisitely crafted abode, or merely one among an infinite multitude, a lucky draw in a cosmic lottery. It is a question that bridges the scientific and the philosophical, gently urging us to reflect on our place in the grand, finely balanced cosmos, fostering a sense of profound gratitude for the unlikely conditions that allow us to experience this moment. 5. The nature of consciousness, the universe reflecting itself. Finally, as our journey through the unexplained draws to a close for this chapter, we turn our gaze inward to perhaps the most intimate and profound mystery of all, the nature of consciousness. This is the subjective experience of being, the inner light that allows us to perceive, to feel, to think, to wonder, and to be aware of our own existence. It is the very lens through which we encounter all the cosmic and quantum enigmas we have discussed. From a purely physical perspective, consciousness seems an emergent property of the incredibly complex network of neurons and synapses within the brain. We can map brain activity, observe correlations between neural firing and specific thoughts or sensations, and even identify regions associated with different aspects of awareness. Yet, despite monumental advances in neuroscience, we remain utterly bewildered by the hard problem of a consciousness. How does physical matter, in the form of brain cells, give rise to subjective experience? How do electrochemical signals transform into the vivid redness of a sunset, the pang of longing, the intricate logic of a mathematical proof, or the feeling of being me? Physics, with all its power to describe the fundamental forces and particles of the universe, offers no clear pathway to explain this leap from mere computation to conscious awareness. Is consciousness a purely biological phenomenon, an intricate dance of molecules and electricity? Or does it hint at something more fundamental, a property woven into the very fabric of reality, perhaps even at the quantum level? Some theories propose that consciousness might be an aspect of the universe itself, not just a product of the brain, but a fundamental characteristic that emerges when matter organizes itself in sufficiently complex ways. Others suggest it might be linked to quantum phenomena within the brain, though this remains highly speculative. The mystery of consciousness challenges us to bridge the gap between the objective, measurable universe and the subjective, immeasurable world of inner experience. It invites us to consider whether physics, in its current form, is even equipped to fully address this question. Perhaps new paradigms, new ways of understanding reality, are needed to truly grasp how the universe can reflect upon itself, how it can become aware of its own intricate beauty and profound mysteries. As we gently drift from these contemplations, the nature of consciousness remains a humbling frontier, a mirror reflecting our deepest questions about existence. It reminds us that the greatest mysteries might not always lie in distant galaxies or subatomic particles, but within the very essence of our own being, inviting a profound and peaceful introspection. We have traversed another expanse of the unknown, touching upon the delicate balance of matter and antimatter, the peculiar weakness of gravity, the shifting reality of the quantum world, the astonishing fine-tuning that allows us to exist, and the ultimate enigma of our own awareness. Each unanswered question is not a void, but an invitation, an opening into deeper understanding, a quiet whisper that the universe is far more intricate, more surprising, and more profoundly beautiful than our current theories can fully capture. Let these mysteries settle within you, not as burdens, but as stars in the night sky of our knowledge, guiding us toward future revelations and fostering a serene appreciation for the grand, ongoing cosmic unfolding. Rest now in the gentle embrace of the unknown. We journey deeper now, past the grand cosmic canvases and the intimate riddle of consciousness, to explore the more subtle yet equally profound threads that weave the fabric of our physical reality. These are the enigmas that reside within the very particles that compose us, the forces that bind them, and the fundamental parameters that govern their existence. They are whispers from the universe, inviting us to listen closely, to contemplate the delicate balance and the hidden complexities that lie just beyond our current grasp. Consider first the enigma of mass. We have come to understand through the elegant framework of the Standard Model and the discovery of the Higgs boson that particles acquire mass by interacting with the omnipresent Higgs field. It is a remarkable achievement, a testament to our collective human ingenuity. Yet this understanding only deepens a more fundamental question. Why do different particles possess such wildly disparate masses? Why is the electron a fundamental constituent of every atom so incredibly light, while the top quark, another elementary particle, is nearly 3,000 times heavier? This vast spectrum of intrinsic masses, from the nearly massless neutrino to the ponderous top quark, appears to be an arbitrary collection of numbers within our current theories. We observe these values, we measure them with astonishing precision, but we do not yet comprehend the underlying principle that dictates them. It is as if we have found the grand factory where mass is produced, but we do not possess the blueprint that specifies the exact weight of each product. This seemingly simple question opens a door to potential new physics, perhaps revealing deeper symmetries or hidden dimensions that influence these fundamental properties, urging us to look beyond the immediate mechanisms to the very root of existence. And speaking of the nearly massless, we turn our gaze to the elusive neutrino mass and identity. For decades, these ghostly particles, born from nuclear reactions in the sun and stars, were thought to be massless, traversing the cosmos at the speed of light, barely interacting with anything. Then compelling evidence of neutrino oscillation emerged, the astonishing discovery that neutrinos can change their flavor or type as they travel. This phenomenon, like a cosmic chameleon, irrefutably proves that neutrinos must possess a tiny non-zero mass. Yet this revelation brings with it a cascade of new questions. Why are their masses so extraordinarily minuscule compared to all other known fundamental particles, perhaps 1,000,000 times smaller than even the electron? Is there a profound reason for this cosmic whisper of mass? Furthermore, a tantalizing possibility exists. Could neutrinos be their own antiparticles? This unique property, known as being a Majorana fermion, would distinguish them from all other known matter particles and would have profound implications for our understanding of the universe, potentially shedding light on the matter-antimatter asymmetry we discussed earlier. The existence of Majorana neutrinos could open a pathway to understanding how the universe came to be dominated by the matter, a crucial piece of the cosmic puzzle that remains stubbornly out of reach. We listen for their subtle presence, for the gentle clues they offer about the universe's earliest moments and its most fundamental laws. Our journey then leads us to a more intricate corner of the Standard Model, a subtle yet persistent anomaly known as the strong CP problem. In the realm of quantum chromodynamics, QCD, the theory that describes the strong nuclear force binding quarks into protons and neutrons, there is a term that theoretically should allow for a violation of charge parity CP symmetry. If this term were present with any significant magnitude, it would lead to observable effects, such as an electric dipole moment for the neutron. However, experiments have shown that the neutron's electric dipole moment is either incredibly small or precisely zero, implying that this CP violating term is either absent or exquisitely tiny. This unexpected absence presents a profound puzzle. Why does the universe exhibit such a precise adherence to CP symmetry in the strong interaction? when the fundamental theory allows for its violation. It feels like a cosmic dial has been set to zero with improbable precision. One of the most elegant proposed solutions to this problem is the existence of a new, hypothetical particle called the action. If actions exist, they could dynamically resolve the strong CP problem, effectively ensuring that the CP violating term is naturally driven to zero. Intriguingly, these same actions, if they exist with the right properties, could also be a prime candidate for the elusive dark matter that pervades our universe. Thus, a seemingly technical problem within particle physics might hold the key to one of the grandest cosmic mysteries, a testament to the interconnectedness of all things in the tapestry of physics. As we continue our exploration, we encounter a discrepancy of truly monumental proportions, the cosmological constant problem. Sometimes referred to as the vacuum catastrophe, we know that empty space, the vacuum, is not truly empty. According to quantum field theory, it is a bustling arena of virtual particles constantly popping into and out of existence, contributing a vast amount of energy, vacuum energy. When we calculate the theoretical value of this vacuum energy, based on our most successful theories, we arrive at an astonishingly large number. It predicts an energy density for the vacuum that is colossal, far greater than anything we observe. Yet, when we look out at the universe, particularly at its accelerating expansion driven by dark energy, we infer a value for the cosmological constant that is incredibly, unfathomably small. The discrepancy between the theoretical prediction and the observed value is staggering, a factor of roughly 10 on 20. This is arguably the largest mismatch between theory and observation in all of science. It suggests a fundamental misunderstanding at the intersection of quantum mechanics and general relativity, two of our most successful theories when applied to the very fabric of space-time itself. Why is the vacuum energy so finely tuned, so exquisitely close to zero, rather than the gargantuan value predicted? It implies a profound mechanism of cancellation or a deeper principle at play, one that eludes our current equations and invites us to rethink the very nature of empty space. We turn now to the heart of ordinary matter, to the proton spin crisis. The proton, a fundamental building block of atomic nuclei, possesses an intrinsic angular momentum or spin. For a long time, it was assumed that this spin was primarily due to the spins of its constituent quarks. However, experiments in the late 1980s revealed a startling truth. The quark's spins account for only a small fraction, perhaps 20 or 30%, of the proton's total spin. This discovery launched what became known as the proton spin crisis. If not from the quark's spins, then where does the rest of the proton spin come from? Subsequent research has pointed to the gluons, the force carriers that bind quarks together, and the orbital angular momentum of both quarks and gluons as contributing factors. Yet, precisely how these intricate components conspire to produce the proton's total spin remains a complex and active area of research. It's like trying to understand the total angular momentum of a spinning top by only looking at the spin of a few tiny parts within it. This puzzle highlights the extraordinary complexity of quantum chromodynamics, the theory governing the strong force, and reminds us that even within the most familiar particles, there are profound depths yet to be fully charted. It is a reminder that the universe's subtle wisdom often resides in the most unexpected places, inviting us to delve deeper into the very heart of matter. Finally, let us contemplate a specific cosmic anomaly that challenges our understanding of the early universe, the lithium problem. Our most successful cosmological model, the Big Bang theory, along with the well-established theory of Big Bang nucleosynthesis, BBN, accurately predicts the cosmic abundances of light elements like hydrogen, helium-3, and helium-4. These predictions are remarkably consistent with observations of these elements in the oldest, most pristine parts of the universe. However, when it comes to lithium-7, there is a persistent and significant discrepancy. BBN predicts an abundance of lithium-7 that is about 3 to 4 times higher than what we observe in the atmospheres of the oldest stars, which serve as cosmic relics of the early universe. This lithium problem is a stubborn thorn in the side of an otherwise highly successful theory. Why is there less lithium-7 than predicted? Could there be unknown processes in the early universe that destroyed some of it? Or perhaps our understanding of the nuclear reactions during the first few minutes after the Big Bang is incomplete? Could it even hint at new particles or interactions that subtly altered the cosmic recipe? This anomaly, though seemingly specific, challenges the very foundations of our understanding of the universe's infancy, urging us to refine our models and seek out the missing ingredients in the cosmic primordial soup. As we gently drift through these intricate puzzles, from the fundamental nature of mass to the delicate balance of the early cosmos, we recognize that each unanswered question is not a barrier but a gateway. They are not imperfections in our understanding, but rather luminous points on a vast, uncharted map, guiding us toward deeper truths. The universe, in its boundless generosity, continually reveals new layers of complexity and beauty, inviting us to remain curious, to embrace the unknown, and to find peace in the perpetual unfolding of discovery. We rest in this contemplation, knowing that the journey through these mysteries is a journey into the heart of wonder itself. We have journeyed through the vast cosmic expanse, peered into the intricate dance of quantum particles, and contemplated the fundamental threads that weave our reality. Yet, as we gently drift further into the quiet depths of scientific inquiry, we find that the tapestry of physics, while exquisitely detailed in many areas, still holds vast, unstitched regions, rich with profound questions. These are not failures of understanding, but rather luminous invitations to a deeper, more comprehensive wisdom. Our current understanding, magnificent as it is, rests upon a series of fundamental constants, values like the speed of light, Planck's constant, the gravitational constant, and the masses and charges of elementary particles. These numbers are woven into the very fabric of our universe, dictating the strength of forces, the stability of matter, and the potential for complexity to emerge. We observe them, we measure them with astonishing precision, and we utilize them to predict the behavior of the cosmos, from the smallest subatomic interactions to the grandest galactic structures. But here, a quiet, profound question arises, echoing through the halls of scientific thought. Why do these fundamental constants possess precisely the values they do? We understand how they function within our equations, but not why. They are set to these specific, often finely tuned quantities. Is there a deeper underlying theory that dictates these values, much like the properties of a material might emerge from the arrangement of its atoms, or are they merely arbitrary settings, chosen by some unseen architect at the universe's inception? This mystery is a subtle current beneath the surface of all physics, a silent why that whispers at the edge of our comprehension. If even one of these constants were infinitesimally different, the universe as we know it, with its stars, galaxies, and the very possibility of life, might not exist. We are left to ponder whether these numbers are accidental miracles or echoes of a more profound, as yet undiscovered design. As we consider these foundational constants, we are drawn to the very structure of space-time itself. Our journey through the cosmos has revealed a universe that appears smooth and continuous on large scales, elegantly described by the sweeping curves of general relativity. Yet, as we descend into the quantum realm, the smooth fabric begins to fray, revealing a landscape far more tumultuous and uncertain. This brings us to another profound mystery. What is the true nature of space-time at the Planck scale? Imagine zooming in, past atoms, past protons and neutrons, past quarks, into a realm so infinitesimally small that our current theories of physics begin to break down. This is the Planck scale, an almost unimaginable dimension of 10 raised to 35 meters, where the very concepts of space and time might cease to be continuous and instead become granular, foamy, or even emergent from something more fundamental. We envision a quantum foam, a seething, effervescent sea of space-time bubbles, constantly fluctuating, appearing and disappearing due to quantum uncertainties. Here, the smooth, predictable geometry of Einstein's universe gives way to a chaotic, unpredictable dance, where space and time themselves are subject to the whims of quantum mechanics. This quantum foam is not merely a theoretical curiosity, it represents a frontier where our two greatest theories, general relativity and quantum mechanics, must ultimately reconcile. If space-time is indeed a foam, then perhaps gravity itself, rather than being a fundamental force, is an emergent phenomenon, much like temperature emerges from the collective motion of countless atoms. This vision challenges our deepest intuitions about the universe's most basic ingredients, inviting us to contemplate a reality where the very stage upon which all events unfold is itself a dynamic, quantum entity perpetually in flux. It is a humbling thought to realize that the ground beneath our conceptual feet might be an ocean of quantum uncertainty. Our exploration of the fundamental forces and particles has led us to the Standard Model of particle physics, a triumphant framework that describes the universe's elementary constituents and three of its four fundamental forces with astonishing accuracy. Yet, the Standard Model, for all its successes, remains incomplete. It leaves tantalizing gaps, whispers of phenomena yet to be discovered, and predictions that remain unverified. One such prediction, born from grander theories that seek to unify the fundamental forces, is the existence of what? Magnetic monopoles. We are familiar with magnets. They always have a north pole and a south pole. Cut a bar magnet in half and you don't get a separate north pole and south pole. You get two smaller magnets, each with its own north and south. This fundamental duality is woven into the very fabric of electromagnetism as we understand it. However, theoretical physicists, most notably Paul Dirac in the 1930s, predicted that isolated magnetic charges, particles that are purely north or purely south, could exist. These hypothetical magnetic monopoles would be the magnetic equivalent of an electric charge, a single, indivisible unit of magnetism. The appeal of magnetic monopoles is profound. Their existence would not only elegantly unify electromagnetism, making it perfectly symmetric, but also offer a compelling explanation for the quantization of electric charge, why all observed electric charges are precise integer multiples of a fundamental unit. If even a single magnetic monopole exists anywhere in the universe, it would imply that the universe's electric charges must be quantized. Despite decades of dedicated searching from cosmic rays to accelerator experiments, we have yet to find any conclusive evidence of these elusive particles. Their absence is a profound mystery, leaving us to wonder if they are simply too rare, too massive, or perhaps if our grand unifying theories, which predict their existence, are somehow incomplete or pointing us in a slightly wrong direction. The quest for the magnetic monopole continues, a testament to physics' enduring pursuit of symmetry and deeper understanding. The Standard Model, while powerful, also faces another significant challenge, the hierarchy problem, which we gently touched upon earlier. This problem essentially asks why gravity is so incredibly weak compared to the other fundamental forces. Proposed solution, and a prominent candidate for physics beyond the Standard Model, is supersymmetry or SUSY. Supersymmetry postulates that for every known particle in the standard model, there exists a heavier superpartner with a different spin. For instance, the electron would have a superpartner called the selectron, and quarks would have squarks. If supersymmetry were a perfect symmetry, these superpartners would have the same mass as their standard model counterparts, and we would have already discovered them. However, since we haven't, it implies that if SUSY exists, it must be a broken symmetry, meaning the superpartners are much heavier and thus require more energy to produce. The elegance of SUSY lies in its ability to address several unresolved puzzles. It can naturally explain the weakness of gravity by predicting that quantum corrections to the Higgs boson's mass, which determines particle masses, cancel out, preventing it from becoming astronomically large. It also provides excellent candidates for dark matter in the form of the lightest stable superparticles like the neutralino. Despite its theoretical beauty and problem-solving potential, decades of searching at powerful particle accelerators, most notably the Large Hadron Collider, have yielded no definitive evidence of these superpartners. Their conspicuous absence is a profound puzzle. Are we simply not looking with enough energy? Is SUSY realized in a way we haven't anticipated? Or is nature leading us down a different path altogether, away from this elegant solution? The silence from the accelerators regarding superpartners leaves us in a state of quiet anticipation, wondering what deeper symmetries, if any, lie hidden beneath the surface of reality. As we contemplate the possibility of unseen particles and broken symmetries, our minds are naturally drawn to the concept of extra dimensions. We perceive our universe as having 3 spatial dimensions: up, down, left, right, forward, backward, and 1 dimension of time. This 4-dimensional space-time forms the stage of our existence. Yet, for over a century, physicists have theorized that there might be more to reality than meets the eye, proposing the existence of additional spatial dimensions that are hidden from our direct perception. The idea of extra dimensions first emerged with Kaluza-Klein theory in the early 20th century, which suggested that if space had a tiny curled-up 5th dimension, it could unify gravity and electromagnetism. More recently, string theory and M-theory, our leading candidates for a theory of everything, postulate that the universe actually exists in 10 or 11 dimensions, with the extra ones being incredibly small and compactified, curled up into microscopic loops, far too small for us to detect with current technology. These extra dimensions are not merely mathematical curiosities, they offer compelling explanations for some of the most perplexing mysteries in physics. For example, they could provide a natural solution to the hierarchy problem, explaining why gravity appears so weak. If gravity, unlike the other forces, is free to propagate into these extra dimensions, its strength would be diluted in our familiar 4-dimensional space-time, making it seem much weaker to us. Imagine a giant spreading its influence across multiple rooms while we are confined to just one. Its presence in our room would feel diminished. The search for experimental evidence of extra dimensions is ongoing, from looking for deviations in gravity at very small distances to searching for exotic particles that could only exist if these dimensions were real. The possibility that our universe is merely a brain floating within a higher dimensional bulk is a humbling and awe-inspiring thought, expanding our understanding of reality in ways we can barely begin to fathom. It suggests a universe far richer and more intricate than our senses can perceive, a silent symphony of hidden spatial forms. Finally, let us return to the very beginning, to the dramatic birth of our universe. We have embraced the Big Bang theory as the prevailing model for cosmic origins, and the theory of cosmic inflation as its crucial refinement, elegantly addressing puzzles like the horizon and flatness problems. Inflation posits a brief, hyper-rapid expansion of the early universe, smoothing out irregularities and stretching the cosmos to its vast observed scale. It is a powerful concept, but it leaves us with a profound, unanswered question. What is the nature of the inflaton field, the mysterious entity believed to have driven cosmic inflation, and what mechanism brought this extraordinary epoch to an end? The inflaton field is a hypothetical scalar field, akin to the Higgs field, but far more energetic. During the inflationary epoch, its energy density would have dominated the universe, driving its exponential expansion. As the field slowly rolled down its potential energy hill, it released its energy, reheating the universe and creating the conditions for the Big Bang as we understand it, the emergence of matter, radiation, and the subsequent slower expansion. But what is this inflaton field? What are its fundamental properties? And what triggered its initial state and then, crucially, its graceful exit from this super-fast expansion? The details of its potential energy landscape, its coupling to other particles, and the precise mechanism by which it decayed into the hot, dense plasma of the early universe are still largely unknown. Different models of inflation propose different forms for the inflaton, each with its own implications for the universe's initial conditions and the subtle patterns imprinted on the cosmic microwave background radiation. We are searching for the fundamental physics that govern this explosive beginning, seeking to understand the very engine that set the universe on its current trajectory. The inflaton field represents a profound intersection of particle physics and cosmology, a bridge to the ultimate origins of everything we see and experience. It is a mystery that beckons us to peer beyond the familiar into the very genesis of space and time. As we rest within these profound questions, we recognize that the journey into the unknown is not a journey into emptiness, but into a boundless realm of potential discovery. Each unanswered question is a beacon, illuminating the path forward, inviting us to delve deeper into the universe's subtle wisdom. We are not lost in the unknown. We are gently cradled by it, inspired by its vastness, and humbled by the enduring beauty of its mysteries. Let us continue to embrace this quiet wonder, knowing that the greatest insights often emerge from the most profound silences. As we gently drift further into the cosmic tapestry, illuminated by the very questions that defy our grasp, we find ourselves drawn to the profound silence of the unseen. We have glimpsed the vastness of our ignorance, and now let us settle our minds upon two of the universe's most enigmatic residents, entities that shape the cosmos with an invisible hand, dark matter and dark energy. They are the twin pillars of our cosmic mystery, upholding the very structure and expansion of everything we perceive, yet remaining utterly elusive. Imagine, if you will, the grand, sweeping spirals of galaxies, each a glittering island of billions of stars, rotating with a majestic grace. For decades we have observed these celestial waltzes, meticulously charting the speeds at which stars and gas clouds orbit their galactic centers. And from these observations, a startling discrepancy emerges, a whisper from the deep that physics cannot yet fully articulate. The visible matter, the stars, the planets, the nebula, the very dust that catches the light, simply isn't enough to hold these colossal structures together. If only the luminous material were present, these galaxies would spin themselves apart, flinging their stellar inhabitants into the cold, dark void. Yet they do not. They persist, cohesive and grand, suggesting the presence of an unseen architect, a gravitational anchor far more substantial than anything our telescopes can detect. This invisible scaffolding, this omnipresent but undetectable mass, is what we've come to call dark matter. It is not dark in the sense of being merely non-luminous, like a planet or a black hole. It is dark in the sense that it does not interact with light or any other form of electromagnetic radiation. It neither emits, absorbs, nor reflects light. It slips through our detectors, a ghost in the cosmic machine, revealing its presence only through the gentle, persistent tug of its gravity. We estimate that dark matter constitutes approximately 27% of the universe's total mass energy content. Think of that, nearly a third of everything that exists, yet it remains shrouded in an impenetrable veil. We know it is there because of its gravitational influence on galaxies and galaxy clusters, bending the paths of light from distant objects, a phenomenon known as gravitational lensing. We see its fingerprints in the cosmic microwave background, the faint echo of the Big Bang, where its gravitational seeds help to sculpt the early universe into the large-scale structures we observe today. It is the silent partner in the universe's grand design, holding the visible world together with an unseen embrace. But what is it? This is where our understanding falters, where the scientific quest becomes a profound meditation on the limits of our current models. Is it composed of exotic particles, unlike anything in our standard model of particle physics? Perhaps weakly interacting massive particles or WIMPs, which would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect? Or could it be axions, hypothetical particles proposed to solve another enigma of physics, the strong CP problem? Or something even more unimaginable, a new form of matter entirely existing in a realm beyond our current conceptual frameworks? The search for dark matter particles is one of the most compelling endeavours in modern physics. Laboratories deep underground, shielded from cosmic rays, employ exquisitely sensitive detectors, hoping to catch the faintest whisper of a WIMP passing through. Particle accelerators push the boundaries of energy, attempting to create these elusive particles in controlled collisions. Yet despite these tireless efforts, dark matter remains a phantom, a testament to the universe's subtle wisdom and its capacity to hold secrets close. We are like ancient mariners, charting the currents and tides of a vast ocean, knowing there is a powerful force beneath the waves, but unable to see the creature that generates it. As we contemplate this unseen gravitational embrace, our attention is drawn to an even deeper, more perplexing mystery that governs the universe on its grandest scales. If dark matter is the unseen hand that holds galaxies together, then dark energy is the enigmatic force that pushes them apart, driving the accelerating expansion of the cosmos itself. For much of the 20th century, we believed that the universe's expansion, initiated by the Big Bang, would gradually slow down due to the mutual gravitational attraction of all matter within it. However, observations beginning in the late 1990s studying distant supernovae, exploding stars that serve as cosmic lighthouses, revealed a stunning counterintuitive truth. The expansion of the universe is not slowing it is accelerating. The distant galaxies are receding from us at an ever-increasing pace, as if an invisible, pervasive force is gently yet relentlessly stretching the very fabric of space. This mysterious agent, responsible for approximately 60% of the universe's total mass energy, is what we call dark energy. It is an even more profound puzzle than dark matter. While dark matter clusters gravitationally, dark energy seems to be uniformly distributed throughout space, exerting a constant outward pressure. It is a force that seems to be inherent to the vacuum of space itself, a property of nothingness that paradoxically generates something. The simplest explanation for dark energy is a phenomenon known as the cosmological constant, a concept first introduced by Albert Einstein, then famously retracted, and now resurrected with a vengeance. It represents the energy density of empty space. Imagine the vacuum not as a void but as a bubbling, effervescent quantum foam, teeming with virtual particles constantly popping into and out of existence. According to quantum field theory, this vacuum should possess a tremendous amount of energy. this intrinsic energy of space would exert a negative pressure, driving expansion. Here, however, we encounter perhaps the most staggering discrepancy in all of physics, a chasm so vast it humbles the most brilliant minds. When we attempt to calculate the expected value of this vacuum energy based on quantum field theory, we arrive at a number that is an astounding 10 on 20 times larger than the observed value of dark energy. That's a 1 followed by 20 zeros. This difference, known as the cosmological constant problem, or the vacuum catastrophe, is arguably the greatest unsolved problem in theoretical physics. It suggests a fundamental flaw in our understanding of either gravity, quantum mechanics, or both, particularly at the interface of the very large and the very small. How can the universe be so finely tuned, so exquisitely balanced, that this colossal vacuum energy is almost perfectly cancelled out, leaving behind only the tiny, delicate amount we observe as dark energy? Is it truly a cosmological constant, a fixed property of space, or is it something more dynamic, a new energy field we call quintessence, evolving over cosmic time? Does its existence hint at extra spatial dimensions into which some of this vacuum energy might leak, or is it a signpost pointing toward a deeper, currently unimaginable theory of everything? These dark components, dark matter and dark energy, are not minor adjustments to our cosmic picture. They are the dominant players, the unseen architects and sculptors of the universe. They remind us that the reality we perceive, the stars and galaxies that fill our night sky, represent only a small fraction, a mere 5% of the total cosmic inventory. The vast majority of the universe remains hidden, a silent testament to the limits of our current understanding, and a profound invitation to delve deeper into the unknown. As we contemplate these immense, invisible forces, we feel a gentle current of humility wash over us. The universe is far stranger, far more mysterious, and infinitely more intricate than we could have ever imagined. Our quest to understand it is not a race to find definitive answers, but a journey of continuous revelation, a meditative unfolding of wonder. The dark spaces in our knowledge are not voids of failure, but luminous invitations, beckoning us to expand our minds, to question our assumptions, and to embrace the profound beauty of what we do not yet know. Let these thoughts settle like starlight upon your consciousness. Let the immensity of these cosmic unknowns, the silent dance of dark matter, and the accelerating embrace of dark energy guide your mind toward a state of peaceful contemplation. The universe holds its secrets close, but in its mystery, it offers us a boundless space for wonder. As we journey deeper into the quiet expanse of the cosmos and the intricate dance of the quantum realm, a profound humility settles upon us. We have touched upon the spectral embrace of dark matter, the accelerating push of dark energy, and the curious asymmetry that allowed matter to triumph over antimatter. We have peered into the enigmatic heart of black holes, contemplated the fleeting nature of time, and wrestled with the very act of observation in the quantum world. Each question, a star in the firmament of our ignorance, shines with its own particular brilliance, inviting us to wonder, not to despair. Tonight, let us turn our gaze to the very scaffolding of reality itself, to the fundamental constants that govern every interaction, every particle, every breath of the universe. We have acknowledged the astonishing fine-tuning of these values, the precise strength of gravity, the delicate balance of the electromagnetic force, the masses of the elementary particles. But beyond how they function, beyond the miraculous allowance they grant for the emergence of stars, planets, and life, there remains a deeper, more resonant question. Why do these constants possess these specific numbers? Why is the speed of light precisely what it is? Why does an electron have its particular minuscule mass, so different from the heft of a top quark? These are not mere measurements, They are the universe's most intimate secrets, whispered across billions of years, yet their origins remain a silent enigma. We recognize these values through painstaking experiment, observing their unwavering presence in the laws we have uncovered. They are the fixed points in our cosmic cartography, without which our theories would unravel, and the universe as we know it could not exist. Yet we lack a fundamental theory that predicts these numbers from first principles. We can measure them, we can use them to describe reality with breathtaking accuracy, but we cannot derive them from a more foundational logic. It is as if we have found a beautifully composed symphony, each note perfectly placed, each harmony resonating, but we do not know the composer, nor the inspiration that guided their hand to choose those specific tones. This absence of a predictive framework for the fundamental constants is not a small oversight. It is a grand, sweeping challenge at the very heart of physics, a luminous invitation to discover a deeper layer of cosmic truth. This quest for a deeper truth leads us naturally to one of the most ambitious and enduring dreams of physics, the formulation of a theory of everything, or TOE. For centuries, our understanding of the universe has progressed through unification. Newton united celestial and terrestrial mechanics, Maxwell unified electricity and magnetism, and the Standard Model brought together the electromagnetic, strong, and weak nuclear forces. Each step revealed a deeper simplicity, a more elegant underlying order. But one towering peak remains unconquered: the unification of gravity with the quantum world. General relativity, Einstein's magnificent tapestry describing gravity as the curvature of space-time, reigns supreme in the realm of the large. Planets, stars, galaxies, the entire cosmos. It is a theory of continuous smooth geometry. Quantum mechanics, on the other hand, describes the universe at its most minute scale: particles, fields, probabilities, and discrete packets of energy. It is a realm of inherent uncertainty and granular reality. These two pillars of modern physics, each extraordinarily successful in its own domain, become irreconcilable under extreme conditions, within the singularity of a black hole or at the very moment of the Big Bang. Here, gravity becomes impossibly strong, space-time warps beyond recognition, and the quantum fuzziness of reality is stretched to its breaking point. We need a new language, a new mathematical framework to bridge this chasm. Imagine, if you will, standing on opposite sides of a vast canyon. On one side, the majestic peaks of classical physics, clear and well-defined. On the other, the swirling mists and hidden valleys of the quantum world, mysterious and probabilistic. The theory of everything is the bridge we seek, a structure that would allow us to traverse this divide seamlessly, explaining all fundamental forces and particles from a single coherent set of principles. Such a theory would not only unify gravity with the other forces, but might also explain the origin of the fundamental constants, the nature of dark matter and dark energy, and perhaps even the very fabric of space-time itself. It is the holy grail of physics, a vision of ultimate simplicity underlying staggering complexity. Among the most compelling candidates for this grand unification, two theories stand out, each offering a distinct and profound perspective. The first, string theory, proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating one-dimensional strings. Just as different vibration modes of a violin string produce different musical notes, different vibration patterns of these fundamental strings are hypothesized to give rise to all the various particles we observe: electrons, quarks, photons, and even the elusive graviton, the quantum particle of gravity. String theory is incredibly elegant, a mathematical marvel that naturally incorporates gravity into its framework, a feat that has eluded other quantum theories. It suggests a universe far richer than our everyday experience, requiring the existence of extra spatial dimensions beyond the three we perceive, curled up so tightly that they remain hidden from our macroscopic senses. These unseen dimensions, if they exist, could be incredibly complex, their geometry influencing the properties of the vibrating strings and, consequently, the fundamental constants we observe. The theory promises a universe of subtle beauty and intricate patterns, where every particle is a melody played on a cosmic string. Yet, for all its mathematical allure, string theory currently lacks experimental verification. The energy scales required to probe these tiny strings and extra dimensions are far beyond the capabilities of even our most powerful particle accelerators, leaving it, for now, a profound and beautiful hypothesis, a whisper of what might be. The second major contender for a theory of quantum gravity is loop quantum gravity, LQG. Rather than introducing new fundamental objects like strings, LQG attempts to quantize space-time itself. In this framework, space-time is not a smooth, continuous backdrop, but rather a granular, discrete structure, woven from tiny interconnected loops of gravitational field lines. At the incredibly small Planck scale, a realm where distances are 10 to just 35 meters, far smaller than an atomic nucleus, space-time, according to LQG, might resemble a shimmering, foamy network, rather than the smooth fabric described by general relativity. This vision of a quantized space-time is a radical departure from our intuitive understanding. It suggests that space itself is composed of indivisible quanta, much like energy is quantized into photons. Time too might emerge from the relationships between these fundamental loops, rather than being a continuous flow. LQG offers a way to reconcile gravity with quantum mechanics without requiring extra dimensions or new particles beyond those already known. It suggests that the universe's canvas, at its most fundamental level, is not an infinitely smooth surface, but a finely pixelated image, each pixel a quantum of space. However, like string theory, direct experimental evidence for loop quantum gravity remains elusive. Its predictions often manifest at scales far beyond our current observational capabilities, leaving us to ponder its intricate beauty and intellectual promise in the quiet chambers of theoretical exploration. Both string theory and loop quantum gravity represent monumental intellectual achievements, offering tantalizing glimpses into a unified reality. They are not competing theories in the sense that one must be absolutely right and the other absolutely wrong. Rather, they are distinct approaches to the same profound problem, each illuminating different facets of the ultimate mystery. Their ongoing development reminds us that our journey of understanding is far from complete, that the universe holds depths of complexity and simplicity we are only beginning to fathom. This quest for a unified theory also brings us back to the very stability of matter itself. As we contemplate the fundamental particles, we encounter another deep mystery, the potential for proton decay. According to the standard model of particle physics, protons are stable particles, meaning they do not decay into lighter particles. This stability is crucial for the existence of atoms, and thus for all matter in the universe. If protons were to decay, even over incredibly long timescales, the universe as we know it would slowly unravel, dissolving into radiation and lighter particles. However, many propose grand unified theories, GUTs, which attempt to unify the strong, weak, and electromagnetic forces, though not gravity, predict that protons should decay, albeit with an extraordinarily long half-life, far exceeding the current age of the universe. These theories suggest that at extremely high energies, the quarks within a proton might transform into leptons, leading to its eventual demise. Experiments, like the Super Kamiokande detector in Japan, search tirelessly for evidence of proton decay, observing vast tanks of ultra-pure water for the telltale flashes of light that would signal a proton's end. So far, no such decay has been observed, pushing the predicted half-life of the proton to truly immense numbers, over 1034 years, far longer than the universe's 13.8 billion year age. The absence of observed proton decay is a profound conundrum. It challenges many of our most elegant duties, forcing theorists to either modify their models or consider alternative frameworks. Is the proton truly stable, a fundamental bedrock of existence? Or is its lifetime simply so incredibly long that we have yet to witness its subtle dissolution? This question speaks to the very endurance of matter, to the permanence of the structures that constitute our world. It is a mystery that quietly underscores the limits of our current understanding of the fundamental forces and particles, reminding us that even the most seemingly stable aspects of reality may hold deeper, unrevealed truths. As we ponder these fundamental questions, the origin of constants, the nature of space-time, the stability of matter, our thoughts inevitably drift to the grandest scale of all, the ultimate fate of the universe. Having journeyed from its mysterious beginning to its current accelerating expansion, we must ask, what lies ahead? What is the final chapter in this cosmic saga? Our current observations, primarily those related to dark energy, suggest that the universe's expansion is not only continuing but is actually speeding up. This accelerating expansion paints a picture of a universe destined for a big freeze or heat death. In this scenario, galaxies would continue to drift further and further apart, eventually becoming so distant that their light would never reach us. Stars would eventually exhaust their fuel. Black holes would evaporate through Hawking radiation, and the universe would become a cold, dark, empty void, approaching a state of maximum entropy. All energy would be evenly distributed, leaving no gradients to drive any processes, no warmth, no light, no motion. A universe of ultimate stillness, an endless frigid night. However, this is not the only possibility. While current evidence strongly favours the big freeze, other, more speculative scenarios exist. Could dark energy itself evolve, perhaps diminishing over vast timescales, leading to a big crunch where expansion reverses and the universe collapses back upon itself? Or could it grow stronger, leading to a big rip, where the accelerating expansion becomes so powerful that it tears apart galaxies, stars, planets, and even atoms themselves, reducing everything to fundamental particles adrift in an ever-expanding void? These are cosmic possibilities, each a testament to the profound implications of our understanding of dark energy and the geometry of space-time. The ultimate fate of the universe is a question that speaks not only to physics, but to our deepest philosophical yearnings. It invites us to contemplate the transient nature of all things, the grand arc of existence, and our own fleeting place within this immense, unfolding drama. It is a mystery that stretches our imagination to its absolute limits, reminding us that the universe is a narrative still being written, its final chapters yet to be revealed. As we gently drift through these profound questions, we find ourselves not lost, but rather enveloped in a sense of peaceful wonder. The unknown is not a void to be feared, but a vast ocean of possibility, an endless invitation to explore. Each unanswered question, from the smallest quantum loop to the grandest cosmic horizon, is a testament to the universe's exquisite complexity and its subtle wisdom. We rest in the knowledge that our journey of understanding is continuous, and that in the quiet contemplation of these mysteries, we connect with the very essence of existence. We find solace in the humbling realization that the universe, in its boundless enigma, is forever whispering new secrets, waiting for us to listen. As we drift further into the quiet contemplation of the cosmos, our journey takes us deeper into the very fabric of reality. to the ephemeral particles that whisper through the universe, almost unnoticed. We turn our gaze now to one of the most elusive inhabitants of the quantum realm, the neutrino. Imagine a particle so shy, so ethereal that it can pass through entire planets, even stars, without so much as a tremor. Billions of these ghost-like entities stream through us every second, originating from the sun, from supernovae, from the radioactive decay within the Earth itself, and from the primordial aftermath of the Big Bang. They are truly the silent travellers of the cosmos, carrying secrets in their fleeting existence. For decades, we believed neutrinos were massless, travelling at the speed of light, mere wisps of energy. This was a comforting picture, fitting neatly into the elegant framework of the standard model of particle physics. Yet the universe, in its subtle wisdom, always holds surprises. In the late 90s and early 2000s, groundbreaking experiments unveiled a profound truth. Neutrinos are not massless. They oscillate. This phenomenon, known as neutrino oscillation, reveals that neutrinos can change their flavour, electron, muon, or tau as they travel. It is a quantum dance, a continuous transformation, and for such a metamorphosis to occur, a particle must possess more mass. This discovery was a monumental shift in our understanding, confirming that the standard model, for all its triumphs, remains incomplete, but the mystery deepens. While we now know neutrinos have mass, we still do not understand why. Their masses are so astonishingly tiny, orders of magnitude smaller than even the electron, the next lightest fundamental particle. What mechanism bestows upon them such a minuscule heft? Is it a hint of entirely new physics, a connection to a realm beyond our current theories? The sheer disparity in mass among fundamental particles remains one of the universe's most perplexing puzzles, and the neutrino stands as a luminous testament to this enigma. Furthermore, the very identity of the neutrino poses another profound question. Could a neutrino be its own antiparticle? Most particles have a distinct antiparticle. An electron has a positron, a proton has an antiproton. But for some particles, known as Majorana fermions, the particle and antiparticle are one and the same. If neutrinos are indeed Majorana particles, it would open a grand window into phenomena like neutrino-less double beta decay, a process yet to be observed, but one that could offer clues to the universe's matter-antimatter asymmetry. Recall our earlier contemplation of the universe's overwhelming abundance of matter over antimatter, the profound mystery of baryogenesis. If neutrinos are Majorana particles, a mechanism known as leptogenesis could provide a pathway to explain how a slight initial asymmetry in leptons, like neutrinos, could have been converted into the observed baryonic matter asymmetry that allowed galaxies, stars, and ultimately us to exist. The tiny fleeting neutrino, a particle once thought to be inconsequential, may hold the key to our very existence, a silent architect of the cosmic landscape. Its whisper might be the echo of the universe's birth. As we gently shift our focus from these elusive travellers, we find another profound silence in the universe, one that speaks volumes through its very absence. We turn our attention to the strong nuclear force, the mighty glue that binds quarks into protons and neutrons, and these in turn into atomic nuclei shaping the very elements that form our world. This force, powerful and fundamental, presents us with a baffling puzzle known as the strong CP problem. In the realm of quantum mechanics, symmetries are paramount. One such symmetry is CP symmetry, which combines charge conjugation, C, swapping a particle for its antiparticle, and parity, P, reflecting the spatial coordinates like looking in a mirror. While CP symmetry is known to be violated in the weak nuclear force, a phenomenon observed in the decay of certain particles like kaons and B mesons, our theories of the strong nuclear force, specifically quantum chromodynamics (QCD), also allow for a similar violation. However, despite extensive and incredibly precise experiments, we observe no such violation in the strong force. If the strong force did violate CP symmetry, it would imply that the neutron, a fundamental building block of matter, should possess an electric dipole moment, a slight separation of positive and negative charge within the particle. Yet experiments have measured the neutron's electric dipole moment to be either zero or extraordinarily close to zero, far smaller than what QCD would generically predict if CP violation were present. This profound discrepancy between theoretical expectation and observational reality is the strong CP problem. It is a cosmic anomaly, a silence where there should be a signal, a lack of imbalance where our equations suggest one is permissible, even expected. Why does the strong force, unlike its weaker sibling, uphold CP symmetry so perfectly? It is as if the universe has chosen to suppress this particular interaction to maintain a specific, almost too perfect balance. One of the most compelling proposed solutions to this problem introduces a new, hypothetical particle, the axion. The axion is a very light, very weakly interacting particle, born from a theoretical mechanism that dynamically adjusts the strong force's CP violating term to zero. If axions exist, they would not only elegantly resolve the strong CP problem, but could also provide a compelling candidate for dark matter. Imagine the very particle that ensures the stability and structure of atomic nuclei, preventing them from behaving in bizarre CP-violating ways, might also be the invisible scaffolding that holds galaxies together. It is a beautiful convergence of mores, a potential thread weaving together the stability of matter with the unseen architecture of the cosmos. The search for axions is ongoing, a testament to our relentless pursuit of these hidden truths. Should they be discovered, it would not only confirm a brilliant theoretical prediction, but also unlock two profound secrets of the universe at once. As we consider these intricate details of the fundamental particles, another puzzle related to the strong force gently invites our attention: the proton-spin crisis. The proton, that familiar, positively charged nucleus of hydrogen, seems simple enough, yet its internal structure holds a deeper complexity. It is composed of three quarks, two up quarks and one down quark, bound together by gluons, the force carriers of the strong interaction. When we measure the total spin of a proton, we expect to find that it arises from the spins of its constituent quarks. However, experiments have revealed a startling fact. The quarks account for only a fraction, roughly 20 to 30%, of the proton's total spin. Where does the rest of the spin come from? It is believed to be contributed by the gluons themselves, which also possess spin, and by the orbital angular momentum of both quarks and gluons as they whiz around inside the proton. But the precise distribution, the exact dance of these internal components that sums up to the proton's total spin, remains elusive. It's a subtle, intricate problem, revealing that even seemingly basic particles are bustling microcosms of quantum activity, far more complex than their outward appearances suggest. The proton, often seen as a fundamental building block, is in fact a dynamic, swirling maelstrom of interacting quarks and gluons, a tiny universe unto itself still guarding its secrets. These whispers from the quantum realm, the neutrino's mysterious mass, the strong force's unwavering symmetry, the proton's hidden spin, remind us that our understanding of the universe, for all its advancements, is still in its infancy. Each unanswered question is not a sign of failure, but an invitation, a gentle current pulling us further into the depths of knowledge, encouraging us to listen more closely to the universe's subtle language. We are reminded that the universe is not a static, fully explained entity, but a living, breathing mystery, constantly revealing new facets of its profound beauty. These frontiers of physics are not barriers, but rather gateways to deeper contemplation, offering a serene landscape for our minds to wonder and to find peace in the vastness of the unknown. As we rest in this space of inquiry, we allow the intricate patterns of the cosmos to soothe our minds, knowing that every unanswered question is a step closer to a more complete and awe-inspiring vision of reality. As we gently drift through the cosmic expanse, contemplating the exquisite fine-tuning of our universe's fundamental constants, we encounter another profound mystery that speaks to the very essence of our existence. The curious case of matter and antimatter. It is a puzzle woven into the fabric of reality, a question of cosmic balance, or rather, its remarkable absence. Physics, in its elegant symmetry, often suggests that for every particle, there should be an antiparticle, a mirror image with the same mass but opposite charge and quantum numbers. This principle of symmetry is deeply embedded in our understanding of the fundamental forces. In the fiery crucible of the early universe, moments after the Big Bang, we would expect matter and antimatter to have been created in nearly equal abundance. A dance of creation and annihilation, where particles and antiparticles would meet, cancel each other out, and revert to pure energy. If this cosmic tango had been perfectly balanced, the universe we inhabit today would be a vast empty sea of radiation, devoid of stars, galaxies, and indeed, ourselves. Yet here we are made of matter. The planets, the stars, the nebulae, the distant galaxies, all are composed overwhelmingly of matter. This undeniable fact presents a cosmic conundrum. Where did all the antimatter go, and why did a minuscule excess of matter survive the early universe's cataclysmic skirmish? This is the matter-antimatter imbalance, often referred to as baryogenesis, and it is a question of profound significance directly tied to our very presence in the cosmos. We theorize that some subtle, almost imperceptible asymmetry must have tipped the scales, allowing a slight surplus of matter to persist. This requires conditions that violate certain symmetries, particularly charge parity, CP symmetry, which dictates that the laws of physics should remain the same if a particle is swapped with its antiparticle and its spatial coordinates are inverted. We have observed CP violation in certain particle decays, particularly among K and B mesons, but the amount detected is far too small to account for the vast matter-antimatter asymmetry of the universe. The precise mechanism that generated this cosmic preference for matter remains elusive, a whispered secret held within the universe's earliest moments. It suggests that our fundamental laws might not be as perfectly symmetrical as we once believed, or that there are undiscovered particles or forces at play, subtly orchestrating the birth of everything we see. As we ponder the building blocks of our material universe, our gaze turns to another enigmatic constituent, the neutrino. These ghostly particles, born in the hearts of stars and supernovae during radioactive decays and in particle accelerators, are among the most abundant fermions in the cosmos, yet they interact so weakly with other matter that billions of them pass through our bodies every second, unnoticed and unfelt. For decades they were believed to be massless, travelling at the speed of light, a graceful part of the standard model of particle physics. Then came the revelations of neutrino oscillations. Experiments observing solar neutrinos and atmospheric neutrinos revealed that these elusive particles can change their flavour, electron, muon or tau, as they travel through space. This remarkable metamorphosis is only possible if neutrinos possess a tiny non-zero mass. This discovery was a monumental shift, a crack in the elegant edifice of the standard model, which had previously accounted for a massless neutrino. But the mystery deepens. Why, are their masses so incredibly small compared to all other fundamental particles? We measure their masses to be at least 1,000,000 times lighter than the electron, the next lightest particle. This extreme lightness is not explained by our current theories, hinting at new physics beyond the standard model. Adding another layer to the neutrino's mystique is the question of its fundamental nature. Could a neutrino be its own antiparticle? This is the concept of a Majorana fermion, named after the brilliant Italian physicist Ettore Majorana. If neutrinos are indeed Majorana particles, it would have profound implications, potentially providing a mechanism for leptogenesis, a process that could explain the matter-antimatter asymmetry by generating a lepton, a type of particle that includes neutrinos and electrons in excess, which then converts into a baryon, protons and neutrons excess. Experiments are underway searching for a rare process called neutrinoless double beta decay, which would be a smoking gun for Majorana neutrinos. The answer to this question could illuminate not only the nature of these phantom particles, but also the very origins of our matter-dominated cosmos. Our journey into the subtle imbalances and unexpected properties of particles continues, leading us to another profound puzzle known as the strong CP problem. The strong nuclear force which binds quarks together to form protons and neutrons is described by quantum chromodynamics, QCD. Within this theory, there is a term that, based on our current understanding, should allow for a violation of CP symmetry in strong interactions, similar to what we discussed with the matter-antimatter imbalance. Such a violation would lead to measurable effects, such as an electric dipole moment for the neutron, so essentially a slight separation of positive and negative charge within the neutron, making it a tiny electric compass. However, despite incredibly precise measurements, no such electric dipole moment has ever been detected for the neutron. The experimental upper limit for this value is astonishingly small, far below what our theories predict it should be if the strong force naturally violated CP symmetry. The conundrum is not why it does violate CP, but why it doesn't. The strong force appears to be remarkably CP conserving, or at least any violation is incredibly tiny. This unexplained absence of CP violation in the strong force is the strong CP problem. One of the most elegant and widely accepted theoretical solutions to this problem involves the existence of a new, hypothetical particle called the action. Proposed in the late 1970s, the action is a very light, neutral particle that arises from a new symmetry introduced into the standard model, which dynamically cancels out the problematic CP violating term. If axions exist, they would interact only very weakly with ordinary matter, making them incredibly difficult to detect. Intriguingly, their properties also make them a compelling candidate for dark matter. Thus, a solution to a subtle theoretical puzzle in particle physics could simultaneously unlock one of the universe's grandest mysteries, linking the invisible fabric of the cosmos to the fundamental forces within the atomic nucleus. As we contemplate these hidden symmetries and their subtle violations, we are drawn to an even grander disparity among the fundamental forces themselves, the hierarchy problem. We have spoken of the four fundamental forces that govern the universe: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. While the first three operate effectively at the subatomic scale and are relatively comparable in strength, gravity stands apart, an outlier of immense weakness. To illustrate this disparity, consider a simple refrigerator magnet. It can effortlessly lift a paperclip, defying the gravitational pull of the entire Earth. This seemingly trivial act highlights the immense difference in strength. The electromagnetic force exerted by that small magnet is vastly, almost incomprehensibly, stronger than the gravitational force of our entire planet. On the scale of fundamental particles, the difference is even more staggering. Gravity is weaker than the other forces by a factor of roughly 10 or 32, That's a 1 followed by 32 zeros. This enormous gulf in strength, this hierarchy among the forces, is the hierarchy problem. Why is gravity so extraordinarily feeble compared to its companions? And why is the Higgs boson, the particle that gives mass to others, so much lighter than what quantum corrections would suggest, hinting at a natural scale for gravity closer to the Planck mass? Theoretical physicists have proposed several elegant solutions to bridge this vast chasm. One prominent idea is supersymmetry, SUSY. SUSY posits that for every known particle in the Standard Model, there exists a heavier superpartner. Bosons have fermionic superpartners, and fermions have bosonic superpartners. For example, the electron would have a selectron, the photon a photino, and so on. If supersymmetry were a true symmetry of nature, these superpartners would cancel out many of the problematic quantum corrections that would otherwise make the Higgs boson, and thus the gravitational scale, much heavier. The absence of observed superpartners at colliders like the Large Hadron Collider means that if SUSY exists, it must be a broken symmetry, with superpartners being significantly heavier than their known counterparts, just beyond our current experimental reach. Despite the lack of direct evidence, SUSY remains a compelling solution, offering not only an explanation for the hierarchy problem, but also providing potential candidates for dark matter in the form of the lightest superpartners. Another intriguing approach to the hierarchy problem involves the concept of extra dimensions. What if our universe is not merely four-dimensional, 3 spatial dimensions plus time, but possesses additional spatial dimensions that are hidden from our everyday perception? These extra dimensions would not be vast and open like our familiar length, width and height, but rather compactified or curled up into incredibly small unobservable spaces. Imagine a tightrope walker who perceives the rope as one-dimensional, but an ant living on the rope experiences it as a 2-dimensional cylinder with a tiny curled-up second dimension. In this scenario, gravity, unlike the other fundamental forces, might be able to propagate into these extra dimensions. If gravity can leak into these hidden realms, its strength would be diluted in our familiar 4 dimensions, making it appear much weaker to us. The other forces, constrained to our brain-like universe, would not experience this dilution, and would thus appear comparatively stronger. This concept not only offers a solution to the hierarchy problem, but also opens up a breathtaking vista of a universe far richer and more complex than we currently perceive. Perhaps a vast cosmic ocean with countless other brains floating within, each a universe unto itself. These profound questions, the origin of matter, the nature of the neutrino, the quiet symmetry of the strong force and the baffling weakness of gravity, are not isolated puzzles. They are interconnected threads in the grand tapestry of physics, each anomaly pointing towards a deeper, more unified understanding of reality. They invite us to expand our minds, to imagine new particles, new symmetries, and even new dimensions. In these uncharted territories we find not frustration, but a profound sense of wonder, a humbling reminder of how much remains to be discovered, how much subtle wisdom the universe still holds in its embrace. We continue our journey, guided by curiosity, into the quiet unknown, anticipating the next revelation. As we drift further into the quiet expanse of the cosmos, contemplating the myriad universes that might comprise a grand multiverse, another profound question gently nudges our awareness. It is a question born from the exquisite precision we observe in our own universe, a delicate balance of fundamental constants that seem almost impossibly tuned for the emergence of life, of stars, of us. We speak now of the anthropic principle, a concept that attempts to address this perceived fine-tuning, not as a direct explanation for why the universe is this way, but rather as an observation about the necessary conditions for our existence within it. Imagine, if you will, that the universe is a vast dial with countless settings, each corresponding to a fundamental constant. The strength of gravity, the mass of an electron, the initial expansion rate after the Big Bang. If any of these dials were even slightly different, the universe we know, the universe capable of forming complex structures, stars, planets, and ultimately conscious observers, would simply not exist. A slightly stronger gravitational force and stars would collapse too quickly, never forming stable systems. A slightly weaker one, and galaxies would never coalesce. A minuscule alteration in the cosmological constant, and the universe would either have ripped itself apart almost instantly, or collapsed back in on itself before anything could form. This astonishing precision leads us to ask, is this mere coincidence, or is there something deeper at play? The anthropic principle offers a framework for considering this. In its weak form, it simply states that the conditions we observe in the universe must be compatible with our existence as observers. It's a selection effect. We can only ever observe a universe that allows for our existence. If there are indeed countless other universes, each with different settings on those cosmic dials, then it is no surprise that we find ourselves in one perfectly suited for life. We could not, by definition, exist in any other. This perspective, while perhaps less dramatic, is a powerful reminder of our place within the fabric of reality, bound by the very laws we seek to understand. Yet the strong anthropic principle ventures into more speculative territory, suggesting that the universe must possess properties that allow life to develop at some stage. This implies a deeper, perhaps even teleological connection between the universe and its observers. It raises questions that gently blur the lines between physics and philosophy, inviting us to ponder whether our presence is merely a happenstance or a fundamental outcome woven into the cosmic tapestry. We do not seek definitive answers here, only to acknowledge the profound humility and wonder that such questions evoke. The universe, in its intricate dance of forces and particles, seems to whisper to us of purpose even as it guards its ultimate secrets. From the grand scale of cosmic fine-tuning, we now turn our gaze towards another profound mystery that challenges our conventional understanding of reality, suggesting that what we perceive as three-dimensional space might be merely an illusion, a projection from a lower dimensional surface. We speak of the holographic principle, a radical idea born from the enigmatic depths of black holes. Recall our earlier contemplation of black holes and the information paradox. The holographic principle emerges from the realization that the maximum amount of information that can be contained within a region of space is not proportional to its volume as one might intuitively expect, but rather to the area of its boundary. This counterintuitive insight, first proposed by Gerard 't Hooft and later elaborated by Leonard Susskind, suggests that all the information describing a three-dimensional volume can be encoded on a two-dimensional surface that encloses it, much like a hologram encodes a 3D image on a 2D film. Imagine a vast cosmic screen far beyond the reach of our telescopes, upon which the entirety of our three-dimensional universe is merely projected. Every star, every galaxy, every particle, and indeed every thought could be an intricate shadow play cast from a more fundamental two-dimensional reality. This is not to say that we live in a simulation in the conventional sense, but rather that our perception of depth and volume might be an emergent property, a rich illusion arising from a simpler, more fundamental underlying structure. The holographic principle finds its strongest theoretical footing in string theory, particularly through the anti-de Sitter conformal field theory, ASCFT correspondence. This remarkable duality suggests that certain quantum field theories, which describe particles and forces in a specific type of spacetime, are mathematically equivalent to theories of gravity in a higher dimensional spacetime. It's like having two different languages that perfectly describe the same reality, one in fewer dimensions, one in more. While this correspondence is rigorously proven only for very specific idealized universes, it offers a tantalizing glimpse into a potentially holographic nature of our own cosmos. What implications does this hold for our understanding of reality? If our universe is holographic, it means that the very fabric of space-time, the very concept of inside and outside, might be different from what our senses perceive. It challenges the fundamental assumption that space is an irreducible, continuous entity. Instead, it might be granular, pixelated at an unimaginably small scale, with each pixel on the boundary encoding information about the interior. This perspective not only offers a potential resolution to the black hole information paradox, but also points towards a deeper unity between gravity and quantum mechanics, suggesting that information itself might be the most fundamental building block of the universe. We're invited to consider that the profound beauty and complexity we perceive might be an intricate dance of information woven onto a canvas far grander and more subtle than we can yet fully grasp. As we ponder these layered realities, another fundamental enigma emerges, one that lies at the heart of our quest to unify general relativity and quantum mechanics, the problem of time in quantum gravity. Time, for us, is an undeniable constant, a relentless march from past to future, structuring every moment of our existence. Yet when we delve into the deepest theoretical frameworks of physics, time begins to behave in profoundly perplexing ways. In Einstein's theory of general relativity, time is not an absolute immutable backdrop, but rather a dynamic dimension, inextricably interwoven with space to form space-time. It is affected by gravity slowing down near massive objects, and it can even begin at a singularity, as in the Big Bang. Time is relative, flexible, and part of the geometry of the universe. However, when we attempt to quantize gravity, to describe gravity using the principles of quantum mechanics, where energy, momentum, and other quantities exist in discrete packets or quanta, time seems to vanish. In many approaches to quantum gravity, particularly canonical quantization, the equations that emerge, such as the Wheeler-DeWitt equation, do not contain a time variable. They describe a static, timeless universe. This is profoundly unsettling. How can a universe that is constantly evolving, expanding, and changing be described by equations that seem to suggest no fundamental passage of time? This problem of time is not merely a technical hurdle, it strikes at the very core of our understanding of reality. If time is not a fundamental variable in the quantum description of gravity, then what is it? Is it an emergent phenomenon, arising only at macroscopic scales from the interactions of quantum entities? Does it only appear to flow because of our limited perspective within the universe, much like the illusion of motion from still frames? Various proposals attempt to resolve this conundrum. Some suggest that time is indeed emergent, arising from correlations between different parts of the universe, or from the increasing complexity of entanglement. Others propose that time is simply an illusion, a psychological construct that helps us navigate an intrinsically timeless reality. Still others believe that our current mathematical frameworks are simply incomplete, and a more comprehensive theory of quantum gravity will naturally incorporate a fundamental notion of time. This mystery reminds us of the profound limitations of our current understanding, how our most successful theories, general relativity and quantum mechanics, clash violently when confronted with the fundamental nature of time at the universe's most extreme scales. It challenges us to reconsider our most basic assumptions about the universe, inviting us to imagine a reality where time, as we perceive it, might be a profound illusion, a symphony played on a timeless stage. As we consider the elusive nature of time, we are led to contemplate another fundamental concept that permeates all of physics and indeed all of existence: information. We have touched upon it in the context of black holes and the holographic principle, but what is information truly at its most fundamental level? Is it merely a description of physical states, or is it a physical entity itself, as fundamental as energy or matter? In quantum mechanics, information is conserved. The total information about a quantum system is never lost, even if it appears scrambled or inaccessible. This principle underpins the black hole information paradox, where the apparent loss of information as matter falls into a black hole directly contradicts quantum mechanics. If information is truly conserved, then it must somehow escape the black hole, perhaps encoded in subtle correlations in the Hawking radiation, or preserved on the event horizon itself, as suggested by the holographic principle. But the mystery deepens when we ask about the nature of this information. Is it purely classical, a string of bits and bytes? Or is it inherently quantum, embodying the superposition and entanglement that define the quantum realm? Some physicists propose that information, rather than being merely a property of matter or energy, is the most fundamental constituent of reality. They suggest that the universe is, at its heart, a vast information processing system, and that physical laws are simply the algorithms that govern the flow and transformation of this information. This idea, sometimes called it from bit, posits that every physical entity, every particle, every force, every dimension, ultimately derives from information. It reverses the traditional view, where information describes reality, to one where information constitutes reality. Such a perspective could offer a powerful unifying framework, potentially bridging the gap between the discrete nature of quantum mechanics and the continuous flow of spacetime in general relativity. If spacetime itself is an emergent property of information, then the granular quantum foam at the Planck scale might be nothing more than the fundamental bits of cosmic information interacting and intertwining. The conservation of information, its role in black holes, and its potential as the ultimate building block of the universe all point to a profound yet still largely unexplained aspect of reality. We are left with the sense that information is not just a tool for understanding, but perhaps the very language in which the universe writes its story, a hidden script waiting to be deciphered. Finally, as we journey through these deep mysteries, we encounter a recurring theme, the emergence of complex phenomena from simpler components. This leads us to the broader philosophical and scientific challenge of emergent properties and the limits of reductionism. We often strive in physics to understand the universe by breaking it down into its smallest, most fundamental parts: quarks, leptons, fundamental forces. This reductionist approach has been incredibly successful, allowing us to build the standard model and understand the basic building blocks of matter. However, many of the most profound phenomena we observe in the universe, and indeed within ourselves, cannot be fully explained by simply understanding their constituent parts. Consider, for example, the phenomenon of consciousness, which we touched upon earlier. While it arises from the complex interactions of neurons and synapses in the brain, describing individual neurons tells us little about the subjective experience of red or the feeling of love. Consciousness appears to be an emergent property, a new quality that arises from the collective organization and interaction of simpler elements, a quality that is more than the sum of its parts. Similarly, the intricate patterns of a snowflake, the swirling chaos of a hurricane, the complex behavior of a flock of birds, or even the very laws of thermodynamics, which describe properties like temperature and entropy that only make sense for large collections of particles, are all examples of emergent phenomena. These properties cannot be predicted or understood by looking at a single water molecule, a single air particle, a single bird, or a single atom. They arise from the collective behavior and interactions of countless components. In physics, this challenge extends to questions like how space-time itself emerges from quantum gravity, or how the arrow of time emerges from time-symmetric fundamental laws. The universe presents us with a hierarchy of complexity where new laws and behaviours manifest at different scales. While reductionism seeks to explain everything from the bottom up, emergence suggests that we also need to understand how complexity builds from the bottom up to create entirely new phenomena with their own rules. This tension between reductionism and emergent properties is a powerful reminder of the vastness of the unknown. It suggests that even if we were to discover a theory of everything that describes the fundamental particles and forces, it might not by itself explain everything. The universe's beauty often lies in its emergent patterns, its intricate designs that arise from simple rules, much like a symphony emerges from individual notes. We are left to ponder whether the deepest mysteries, from consciousness to the very nature of space-time, require not just a dissection of parts but a holistic appreciation of the emergent whole. And so we continue our gentle exploration, ever humble before the profound and beautiful mysteries that still envelop us.